Hi everyone, I'm Shifu Chen from Zhejiang University. Now I present our latest paper visualizing large-scale spatial time series with GeoChron. Many sensors are deployed for monitoring and understanding important spatial-temporal phenomena. Each sensor can generate a spatial time series with a geographic position. Usually, the generated spatial time series will be large-scale in both space and time dimensions. Spatial time series can be directly plotted by their geographic positions, or displayed in a separate view that is coordinated with a map. Yet, such a direct depiction method is not effective for large-scale datasets. Another strategy is to transform ST series by summarizing them into summaries, or by extracting patterns from them. However, the trend narrative and dynamics of ST series and the fundamental features of ST series data are broken into summaries or patterns. Each ST series is not isolated in space and time. Usually, spatially closed ST series exhibit correlated trends within a time period, when the recorded phenomenon evolves over the region within that period. We call such an observation evolution pattern. These patterns offer the possibility that large-scale ST series can be visualized in a pattern-aware and narrative-preserving manner. First, visualizing these patterns enable users to view multiple ST series meaningfully at once, rather than scan many ST series to derive knowledge in their minds. Second, the ST series data are continuous between evolution patterns in adjacent but not overlapping periods. Visualizing such patterns along the timeline can retain the temporal narrative of the trends and dynamics of the involved ST series. The storyline technique is well suited for visualizing evolution patterns. In the storyline on the left, each curve represents a character, and curves are bundled together to form a session, only if the entities are related to each other in the period. By drawing an analogy between an evolution pattern and a session, or an ST series and an entity, the storyline can present evolution patterns over time in a well-organized way, and thereby visualize large-scale ST series. However, two challenges must be addressed to apply the storyline technique to visualize large-scale ST series. First, mining evolution pattern is non-trivial. The temporal trends and spatial context are heterogeneous with different scales and semantics. Moreover, the correlation relationships between two series are highly dynamic. Mining the patterns where multiple series should have many such relations with each other is rather difficult. Second, popular temporal visualizations and spatial visualizations are difficult to integrate into the already compact laid-out storyline. In this study, we propose GeoChron. For the first challenge, GeoChron includes a pattern mining framework. For the second challenge, GeoChron adopts a two-level visualization. The evolution pattern mining has 4 steps. First, the data is sliced evenly into time slices. Second, for each time slice, we compute pairwise correlation relations with Pearson's R. Note that we will consider adjacent time slices for smoothness in this step. Third, we construct a spatial temporal network. Each node is an ST series. The each exists if they have a correlation relation and close enough. Recall that ST series belong to the same session if they are correlated in time slice and are close in geographic space with each other. Based on network formulation, these ST series exactly form a community in the relation network. Thus, we detect the communities and consider them as evolution patterns in the storyline. The second, third, and fourth steps are executed for each time slices. The interactive visualization is to encode the temporal dynamics and link them with the spatial context. It has 2 levels. At the first level, we revisit the storyline to encode the temporal dynamics of time series. We first remove the space within the session. Each session is a pattern. It comprises multiple time series segments. To accommodate the compact layout, we encode trends with shades of curves. Finally, we obtain a storyline like this. GeoChron includes a map to provide the spatial context. Each dot on the map represents an ST series. We enable users to interactively color the ST series. The colors of the dots on the map are also updated according to the coloring. In this way, the spatial context and temporal trends are visually linked. At the second level, users can drill down into evolution patterns with evol lengths. Users first brush a rectangle on the storyline to select a time period and sessions. Then, the evol length pops up on the right side of the map. Each session is visualized as a line chart. These line charts are positioned according to the session's positions in the storyline. Evil lens presents the temporal dynamics in details. We have more space for displaying line charts. We also designed the trend motif to depict the trends of the line chart. When users hover over the evil lens, the map shows a convex hull to display the detailed distribution of patterns. We evaluate GeoChron comprehensively. First, we perform real-world case studies.
We first notice several sessions with large sizes and dark strokes. To show their spatial distributions and temporal evolutions, we color these sessions with different colors. In this process, the sessions with more ST series in common tend to receive the same color. These colored ST series are mainly distributed in North China and Yangtze Plain, and ST series with different colors constitute different geographic clusters on the map. There are some high-level interesting observations. First, the red ST series in the BTH region evolved with the purple ones during period A. Afterward, they became uncorrelated during period B. In addition, the orange ST series were strongly correlated throughout the period and sometimes were correlated with the northern purple ST series. Interestingly, they had no correlation with the ST series in the south because no blue ST series was found in the involved sessions. It is probably because the hills between these areas would impede pollution propagation. In North China, a group of spatial temporal series gradually split into 4 over time. The red, green, and purple spatial temporal series all exhibited an increasing trend over time as their strokes became darker. To reveal clear patterns, we further color A1 purple and color A2 black. Then we brush these sessions and obtain the EVO lens. The purple and green spatial temporal series were distributed in the center and geographically close. They correlatively increased, and reached a high level of air pollution, within the first 3 days. Afterward, they became uncorrelated, as the purple spatial temporal series increased, while the green ones fluctuated and decreased. They separated into left and right regions on the map. The black spatial temporal series were less correlated with others, and did not rise very high. It may be because the sea breeze blowing from 3 sides would blow away air pollution quickly. Finally, the red spatial temporal series decreased on the 3rd day, and rose again quickly in the last few days, when the others decreased. It is a hypothesis that in the last few days, another pollution source contributed to pollutants and polluted the BTH region. During period C, severe air pollution occurred in the Yangtze River Delta and its northern region. It is wondered whether there is a propagation process between the 2 regions. We enforce the alignment on session I and obtain the layout. The orange and purple spatial temporal series are placed closer, because their sessions have been aligned with the highest priority. We then brush the related sessions for details. At first, half of the orange spatial temporal series were correlated with the purple ones. Afterward, the orange spatial temporal series appeared in another session because they had a subtle drop during period D. As a result, the orange spatial temporal series reached a high level of air pollution 1 day later than the purple ones. In the last 3 days, the orange and purple spatial temporal series had slightly different trends, and both exhibited subtle declines around 4 p.m. each day. These observations imply that there may be propagation processes of air pollution, from north to south in the first 2 or 3 days. Afterward, the air in both regions was filled with air pollutants. The fluctuation or decline trends in the 2 regions are different, due to their different industrial structure and pollution purification capabilities. We consult historical weather data, and at that time Yangtze River Delta did receive strong cold air from the north, which caused blizzards and brought massive air pollutants.
The user study evaluates the intuitiveness and legibility of GeoChron. We invite 6 participants with diverse background or expertise. They are required to use GeoChron to complete 3 analytical tests. They finally fill out ICET questionnaires. From the results we can see that all participants did understand the GeoChron's visualizations. They can quickly and correctly locate the periods and make descriptions similar to the case. The ICET analysis shows that all participants agreed that GeoChron can provide insights, facilitate exploration, and reveal the essence of data. Due to limited time, please refer to the paper for the ablation study, parameter analysis, and runtime analysis. In summary, we developed GeoChron, an effective technique for visualizing large-scale spatial time series. It adapts the storyline techniques by including a data mining framework and 2-level visualizations. We also demonstrate its successful application to real-world cases. We'd like to thank the funding agencies for their generous support. That concludes my presentation. I'm ready to take questions. Thank you.